ASUS has started to release its Wi-Fi 7 models one after the other, so I decided to buy the already 1-year-old RT-AXE7800 because that's just the type of person I am. Yeah, so if you haven't already read all the reviews available online, then welcome, and you may be in for a treat because I usually test this device a bit different than the rest, as you will see. Okay, so what does the RT-AXE7800 promise to offer? The most important aspect is the third radio band, which operates on the 6 GHz frequency, but we are still limited to the 160 MHz width. Only the Wi-Fi 7 devices have pushed farther, reaching 320 MHz for now. WaveDMA is also supported, and we do get one 2.5 gigabit port which can be used for both WAN and LAN purposes. I don't think that's enough, but ASUS seems to have gotten more generous with its newer devices. It seems that the RT-AXE7800 was not among the lucky ones. I did see that there is support for LAN aggregation, something that is missing on the Expert Wi-Fi EBR63, but I also saw support for WAN aggregation. It's not just the usual failover load balancing algorithms, but actual increased bandwidth, although it's just up to 2 gigabits per second. It's still something. The operating system is also feature-packed, and you can use this device to create an AI mesh network, but I saw that there is no support for Merlin, which is a bit of a shame. Let's now talk about the design of the RT-AXE7800. I admit I have seen better, but I have also seen much worse. The router has a sort of arachnid look, and since the antennas are non-removable, the router comes with all 6 of them folded at the top. You know, just like when a spider curls up its feet after being slapped. I did make a video which shows how easy it is to change the antennas on routers that have them non-removable, but these antennas will be a pain to change due to the wider base. At least the device itself, it's fairly compact, and ASUS has added the option to mount the router on the wall if there is no space on a shelf. As for the LEDs, there are lots of them accurately showing the status of various aspects of the router. They did not go with a single disco light that other brands went with, thank God. Now let's talk about the ports. There is a DC in port on the left, followed by 3 gigabit LAN ports, the third supporting link aggregation with a 4 gigabit port. And this last one can also function as WAN, same as the 2.5 gigabit port that's farther to the right. And then we also get a USB 3.0 port. The usual set of buttons is positioned on the bottom side, and the developers definitely showed their creative side here, which I definitely enjoyed. As for the heat management, ASUS has been very generous with its ventilation holes, both on the upper section as well as on the bottom side. But we're still dealing with passive cooling, so is that enough? I did use a thermal camera to get an idea, and as expected, we can see some warm spots appearing. But that's normal since the heat is being pushed away from the chipsets. The temperature doesn't rise above reasonable limits, and I doubt it will anywhere in the future, so there should be no fears of thermal throttling. ASUS doesn't like you opening up their routers, and they make that very clear when they add those warning stickers on top of the screws. But at least in the US, you should be protected from such transgressions. Well, you should. Anyway, I did open up the RT-AXE7800, and I have documented each step in a dedicated video. The process is fairly straightforward. There are 4 screws that need to be removed, and then use a prying tool to detach the bottom side. Then we should be able to see some heat spreaders on both sides of the PCB, which also need to be taken out, and this does involve detaching the antenna connectors as well. Nothing too complicated though, because no gel or glue or whatever it's called is being used here. Then we get to see the main components. I did go a bit fast through them to keep this video shorter, so pause at any point to get a better view. I have also included a comparison table so you get an idea about how things are different across different models. Now let's see the throughput that I managed to measure using multiple types of client devices. For the 5 GHz radio band, I relied on a laptop equipped with an Intel AX200 as the Wi-Fi 6 client, another laptop with an Intel 8265 and a Pixel 2 XL smartphone as the Wi-Fi 5 client devices. As for the Wi-Fi 6E client, I used a PC that was equipped with a TP-Link TX3000E adapter. Upstream, I saw that the throughput easily broke through the gigabit limit, and as you can see, the Wi-Fi 6E and the Wi-Fi 6 clients managed to offer a very similar performance, at least near the wireless router. That's because both were using the 160 channel bandwidth, and there wasn't that much interference to mess things up. We can see it in the signal attenuation graphic, which also reveals that a measured -86 dB will still allow the two aforementioned client devices to be near 100 megabits per second. Downstream, the Wi-Fi AXE client did a bit better, which was interesting, but it's still an overall decent performance. As for range, we again need to look at the signal attenuation graph, which reveals that at -71 dB we get way more than 100 megabits per second on all clients -1, while at -86 dB we can see that the Wi-Fi 6E client barely managed to offer a couple of megabits per second. Then again, the other clients did much better. When compared to other wireless routers that I tested so far, using the 160 MHz channel width does put the RT-AXE7800 fairly close to the top, just in between the RT-AXE86U Pro and the GT-AXE6000. When using the 80 MHz channel bandwidth, it's a bit less impressive, but then again it's still above 900 megabits per second, so I won't complain that much. Lastly, let's have a look at a longer term performance view and get an idea about the throughput consistency. But before moving forward, I do need to mention that it takes a very long time until the 6 GHz radio gets detected, and I noticed that turning off some settings such as MUMIMO or FDMA and then re-enabling them did help the client see the network a bit faster, as seen in a couple of minutes. We also need to talk about the 2.4 GHz network performance because we do need to use it with older devices and especially anything that's within the smart devices realm. Using the Wi-Fi AXE client, we see very good results, and when compared to other wireless routers that I tested until now, we see that the ASUS RT-AXE7800 falls somewhere in the middle. As for range, the throughput remains fairly consistent up until the signal attenuation doesn't drop below -60 dB. At -76 dB, the smartphone struggled a bit, which makes sense since it's old and barely functional, but the other two clients did surprisingly well. Now that we're done with the single client tests, let's see how well the RT-AXE7800 handles multiple clients, and we will focus on the latency performance. I have used the same set of clients as before and the same server PC, but I have included a signal attenuation measured at each client level to get an idea about the amount of interference that I was dealing with. And yes, I have used the same open source tools developed by Mr. Jim Salter, which you can use as well. You can get it from GitHub. Now let's start with the concurrent 1080p streaming traffic on 5 client devices. We want the latency to be below 50 milliseconds all the time, but only 2 clients stayed near this value for 75% of the time. Both did raise slowly towards 70 milliseconds for about 95% of the time, with a shot above 100 milliseconds for 5% of the time. It's not going to be a bad performance, but the other 3 clients' devices did tend to go near 100 milliseconds for at least 10% of the time. So you can experience some buffering if you try to stream some 1080p videos on a similar set of clients. Let's push it a bit more and run 4K streaming traffic on the same 5 client devices. Unsurprisingly, the latency did raise across all clients, with the same couple of devices trying their best to remain beneath 100 milliseconds for 75% of the time. The rest didn't care and rose above that limit, so it's best to keep the number of clients low if you wish to have a good performance. Or just move a few on the 6 GHz network if there's support for this standard. Next, I wanted to see if the router will handle both 1080p streaming and intense browsing to be run at the same time on all 5 client devices. And as you can see, the 1080p streaming was handled decently well on the Wi-Fi 6E and Wi-Fi 6 clients, which only rose above 100 milliseconds for 1% of the time, while the 2 Wi-Fi 5 clients struggled a bit more. The intense browsing graphic shows that all clients remain beneath 300 milliseconds all the time, which is perfectly fine. We don't want the latency to rise above 1.5 seconds. Then I ran the same test, but I simulated 4K streaming traffic instead of 1080p. And as I anticipated, the 2 clients managed to barely stay below 100 milliseconds for 75% of the time, while the rest went above this limit and even almost reached 250 milliseconds for 1% of the time. Not good. In this case, we need to put some clients on the 6 GHz network and perhaps even rely on an Ethernet cable. The intense browsing graph shows that all clients stayed below 400 milliseconds, which again is an acceptable performance. Moving forward, we changed things a bit and simulated the downloading of a 10 MB file continuously onto client devices. 2 handled intense browsing and 1 for the 4K streaming. Neither of the 2 downloading clients were spectacular, but one did stay below 400 milliseconds for 95% of the time, which I did not expect, to be honest. The 4K streaming client did not do well, but the intense browsing client did remain below the 1.5 seconds limit. The total throughput for the downloading clients was 516.3 megabits per second. Afterwards, I let one client to handle the downloading traffic, 2 for the 4K streaming and 2 for the intense browsing. The latency did get better, but I suspect nobody will be happy downloading stuff when the latency is above 200 milliseconds. The 4K streaming latency was above 100 milliseconds on both clients, which is not good, but the intense browsing clients did well. Next, I limited the number of clients to 3, one for the download traffic, one for the 4K streaming, and one for the intense browsing. And the latency got slightly better than before, but we're still not there. So let's download a 1 megabyte file this time and replace the 4K streaming with voice over IP. There we go. We finally get decent performance, so the conclusion is that you do need to put some heavy QoS limits, spread the clients across the networks, and use cable when possible for the best performance. As a bonus, I added a graph where all client devices were downloading a 10 megabyte file continuously, and the latency is as expected. Since we're done with the throughput and the latency tests, I wanted to put the TrueNAS device that I recently built to good use. So I decided to check how well the RT-AXE7800 works with LACP aggregation of a couple of LAN ports. And then I realized that I had to switch the WAN port to the 2.5 gigabit port in order to let the default LAN 1 and LAN 2 to be aggregated. Why not let me use whichever LAN port I want? The problem is that I have a dilemma which I couldn't figure out. Maybe it's the long day, or it's maybe something silly that I missed, but I seriously don't see the point of LACP aggregation on this router. I can connect the TrueNAS just fine to the two LAN ports, and the links were up and running. So we should get a full 2 gigabits per second, or at least something close to it. But what now? I do have a computer with a 2.5 gigabit port, but where do I connect the cable? All that's left are gigabit ports, so what's the point of aggregating the LAN ports? Again, it's been a very long day, so do let me know in the comments if I missed something ridiculously obvious. It happens more often than I like to admit. Now let's see the WAN performance of the router. It does support load balancing and failovers, so I set up the 2.5 gigabit port as the main one and the 1 gigabit LAN 1 port as the second one. After setting things up, I pinged two domains and disconnected the main cable. It took quite a bit before the RT-AXE7800 switched to the other link, so I checked how long it takes to move back. Only one dropped packet. Not bad. Let's disconnect the main line again. Same performance as before. Yes, so it seems that the router likes to stick more to the main line. But wait a minute, didn't ASUS say that there is support for WAN aggregation? Is this all, or can we actually increase the bandwidth? Apparently this function can be found under WAN internet connection and can be enabled, so the router will use the LAN 1 and LAN 2 to bond the two links. My internet connection doesn't go above 1 gigabit per second, but it's good to know that this feature is available and ready to be used. To check the power consumption of the router, I connected a smart relay and used their dedicated app to see the real-time status data. And this is what it needs for most of the time, not at peak load. After the eye candy layout of the Expert Wi-Fi EBR63, I realized that the layout of the ASUS routers definitely needs a revamp, but we're still getting everything that's needed in the same place we're accustomed to. So there's the general settings on the left where you can check out the AI protection section built and maintained by a third party, the Trend Micro, but which remains included in the price of the router. And trust me, ASUS is one of the few that does this. Then there's the parental controls, which are also powered by Trend Micro and will collect some data. We do get to add devices, block certain categories and schedule the internet access, a feature which again is usually locked behind a subscription. The quality of service is going to let you prioritize which type of application will receive the most bandwidth, and there's also the traffic analyzer by apps and devices. Some of the usual gaming features are missing, so I guess the RT-AXE7800 is not a part of the gaming series. Anyway, we get advanced settings where you can go quite in depth with the configuration and control, especially for the wireless settings. Some of these features have been previously explored, such as the dual WAN and the LACP aggregation, but I also need to mention the VPN support, which covers PPTP, OpenVPN, IPsec and WireGuard. Of course, the VPN Fusion and the Instant Guard are still present as well. Now let's talk about the app. The layout is the same as with most other ASUS routers. The home window shows some status info in the middle, where you can also check the iMesh connections, and I was surprised to see that there was the game mode included as well. The QoS for the devices is more intuitive here than in the web-based interface, since you can choose the priority of each client, while the family section will let you use templates or create profiles for the web access and to set up internet access schedules. Lastly, we get the settings section, which offers some amount of control and configuration, but it still pales in comparison with the web-based advanced settings. Now that we have reached the end, what did I mean when I wrote that it should have been better in the title, you may ask? Well, the router doesn't feel very stable and I kept on getting into weird little bugs here and there, which usually were solved after a reboot, but they're still very annoying. The performance is okay, especially the multi-client latency. The 6 GHz does open up more possibilities. Well, kind of, because ASUS is already releasing its Wi-Fi 7 router series, which I assume will be better. But we'll see. That's all for now. Subscribe to see more of this type of videos. Thank you for watching, and see you next time.